Hello guys, so welcome again to the iitian Gate classes. So here my dear friend, we're gonna start as we have discussed a few topics regarding the axial loading case, and we have also seen the CFOs and bending moment diagram. In this particular lecture, we're gonna start slopes and deflections, and we will see some of the important method, to solve the slopes and deflection problem. What is there in our strength of material? So here I'm just giving you brief introduction about the. So first of all, it is strength of material. In this, my different, we have slopes and deflection topics. Slopes and deflections, right? So this is what we have to discuss. So in this one, very first thing is that we need to know a little bit something about, how the deflection will be there for any particular beam. So we know that we have the different kinds of beam, right? You can take the example of cantilever beam. We can take the example of simply supported beam, overhanging beam. We can also have the example of other categories of the beam also, some fixed beam, some basically we can categorize beams in two broad classifications. One is statically determinate beam and second is statically indeterminate beams. So first of all, I'm showing you right now, this is a statically determinate beams, right? So this is what, when I apply the load, this will be the deflection will be there, right? So you can call this to be deflection curve, or it is broadly known as elastic curve. Elastic curve. Now, to know how to draw the elastic curve, it is very important. So how we have drawn? We have drawn the elastic curve on the basis of bending moment diagram, right? So basically how the bending moment will be varying at any particular section, which is taken at a distance what? X from the free end. So we know that bending moment at this section, XX, will be minus P into X. So it is hogging bending moment. That's why it is going to bend like this only, something like this, right? Now, so here I'm not discussing that thing just because of sake of telling you that how the deflection curve has been plotted based on the bending moment diagram or based on the moment value with the sign. But rather than discussing those things, we are very much concerned about what will be the radius of curvature for this, particular, this one, what we are having. This particular deflection curve or elastic curve, what is going to be the radius of curvature, right? Something like this, and how the radius of curvature will be correlated with this particular deflection curve or elastic curve, right? So we're gonna have, again we're gonna discuss in the bending stress, but right now let me write m by I is equal to sigma by y is equal to E by R. So this is what we have the bending equation, my dear friend. This is what we have the bending equations, right? This is our bending equations. So here in this bending equation, how this m by I is equal to E by R is related? Here they have related by EI by M. So definitely what we are understanding, that we are understanding one thing, the radius of curvature, here R is what? Radius of curvature. Radius of curvature. So definitely we got to know one thing, that the radius of curvature is EI by M, right? Again, this is a very, very important fundamental topic. And we also know that, my dear friend, that, for a very, very small deflections, suppose you have the very small deflections, you have a very, very small deflection. Suppose this is our elastic curve. For a very, very small deflections, this will be, suppose, for example, d theta, right? And if I'm going to project onto this x-axis, this will be dx, and this is going to be, for example, this one will be ds, but what I'm saying you, if the angle will be very, very small, if I project onto the x-axis, it will be very, very similar only, right? So what I can write, d theta can be written as, here we can write d theta as, by the concept of what we can write. If I just take the radius of curvature somewhere here, then what we can write, my different. Suppose this will be d theta. So ds will be equal to r into d theta, right? R is the radius of curvature, and this will be the diagram, right? So here ds is very, very, see, for small deflection, what we can write? ds is almost equal to dx. So dx will be equal to r into d theta. So what we can write d theta by dx, my dear friend? 1 upon r. So here 1 upon r will be ei by m. So what we are getting, my dear friend? D theta by dx will be equal to m divided by ei. In short, we can write m is equal to what? Ei into d theta by dx. Something like this, right? Again, this is a very fundamental relations that we are developing right now. And again, d theta by dx is nothing but, you know, what we have, my dear friend? D theta by dx. See, theta is nothing but the slope, and we can also write d theta as dy by dx. Theta can be written as d theta dy by dx. Slope can be written as something like this. So if I put over here, I will be getting what? M is equal to ei into d square y by dx square. So this is my complete uh, understanding of the bending, basically what? Elastic equations, I would say. How the bending will happen, what will be the bending moment, and what will be the relationship. That is what we have the development. This is the fundamental equations we have. With this fundamental equation, this is a very important equation, right? So let me write once again, m by ei is equal to what? D square y by dx square. A very, very important relations. Sometimes we used to write like this also. Ei into d square y by dx square is equal to what? Mxx. A very fundamental thing of solving the deflection problem. If you want to, somebody will be asking you, just formulate the equations of the deflections. This will be the equation that will be useful. Now, few more things are there, but I will directly jump to the method of solving the deflection and slope problem. The very first method, that is a very basic method and very important method. Very, very important method is moment area method. In this moment area method, my dear friend, when you try to understand the moment area method completely, then we can solve a very tough problem with the help of this particular method within the span of 2 to 3 minutes, right? Try understanding. Moment area method means the name itself is suggesting that we have to draw the bending moment diagram. That is the first thing, right? Now, theorem number one, what it is suggesting right now, the angle between, understand, the angle between the tangents at any 2 points on the elastic curve will be equal to area under m by ei diagram between these 2 points. What is the meaning of that, sir? See, suppose you have the beam. I'm showing you right now, this is a beam, and this beam is supported. Suppose that it is being supported, simply supported beam, and I have considered two sections, A and B, right? And my dear friend, I know that when suppose there will be some loading condition has been applied onto the beam, some deflection will happen. And let's suppose the deflection is occurring something like this. For example, deflection is happening something like this, right? I know it is very difficult to believe that it is a symmetric deflections, because this type of deflection mostly occur when we have applied symmetric load exactly at the middle of the simply supported beam, something like this. But here I'm agree with the fact that it is not a symmetric load, but I'm assuming that right now. So here my different at the point A, draw the tangent at the elastic curve. What I'm saying, draw the tangent. What is this, my different? This is a tangent at A. Draw the tangent at B point also. Draw the tangent at the B point also. What is this, sir? This is the B point. And draw the tangent. Let me draw accurately. Now, try understanding what I'm saying. Draw the elastic curve accurately. This one. This will be the tangent, the green color which I'm showing to you right now. This is a tangent at B point. Getting my point? So this is a tangent at B. This is a tangent at A we have drawn. According to this theory number one, what it is suggesting that whatever the angle is there, right, between these two particular tangent at this particular point, we will be calling that theta B with respect to A. Theta B with respect to A can be written as theta B minus theta A. Everybody know from the vector. And how to read that, my dear friend? How to read that? How we are reading this one? The reading will be meaning. If I just tell you, the meaning of theta B with respect to A will be angle of tangent at B. Angle of tangent at B, measured with respect to measured with respect to tangent at A. That means we have extended the whatever the tangent that is being drawn at point A, we have extended that, and we have taken that as a reference, and we have drawn what this tangent at B is making an angle with respect to tangent at A, something like this. And if I want to write for this point A, then what I will be writing, my different, this is the point A, this is the point B. And what about this angle? This angle will be theta A with respect to B. But how to calculate theta B with respect to A, theta B minus theta A? It is simply M by EI diagram, area of M by EI diagram. Let me write area of M by EI diagram. Sorry, area of M by EI diagram between B and A. Between B and A. This is our a very short conclusion regarding the theory number 1. You will understand the fundamental of this theory 1 and 2 once we discuss the problem. Getting my point? So here we will try to develop some understanding regarding theory number 2. One more thing. When theta B with respect to A has been taken angle, see, it is making this particular tangent at B, green color, is making an angle with respect to tangent at A. In which sense? Anti-clockwise. So if it is anti-clockwise, then anti-clockwise will be taken as positive, because sign convention also we need to follow, Anti-clockwise will be taken as positive, but theta A with respect to B will be clockwise, so that is going to be negative. Automatically you will be getting the answer as negative, right? And one more thing, area of M by EI diagram, when the area of M by EI diagram will be, suppose bending moment diagram is positive, area will also be positive. If it is negative, area will also be negative. Getting my point? Now, theory number 2. Again, theory number 2 is regarding, is what? It is regarding finding the deflections. Regarding finding the deflections. Here, understand the vertical distance between the tangent at A on the elastic curve and the tangent extended from other point equals to the moment of area under M by A diagram. Looking at this statement, it looks very kind of, something like painful for us. But once I will discuss this thing, then you will enjoy this statement. Try understanding. Suppose we have the simply supported beam. I'm just taking the same example. For example, this is the point load, and this is my elastic curve, my different, right? So I'm just taking the point. I'm just taking the point. What I'm just taking the point A. Sorry. This is the point A. This is the point B. Now, my different, try understanding. I'm drawing the tangent at A. I'm drawing the tangent at A. This is the tangent at A. What I'm just telling you, the tangent at B will be something like this. This is the tangent at B. Only 5 minutes it will take. After that, the problem you can enjoy, right? But understanding the statement is very, very important. That is a fundamental requirement of understanding moment area method. So, my dear friend, if I want to find what is this distance, I'm calling delta A with respect to B. Why I'm calling A with respect to B, not B with respect to A? First of all, I have taken the point on elastic curve at the A point, and I have taken the measurement of that particular point with respect to which particular point? The point on the elastic curve which has been extended from the B point. And that is what they have written. The vertical distance between the tangent at A on the elastic curve and the tangent extended from another point B equals to this A with respect to B can be find it out. A minus B can be written as moment of area under M by EI diagram. Under M by EI diagram. Now try understanding, sir, what is the meaning of this? The meaning is quite simple. Once we discuss the problem, then you can understand. That means you might have drawn the moment area between A and B. So you might have drawn the bending moment diagram here. So not only you need to find the area, area into distance of center of gravity of M by EI diagram. What I'm just writing, please make a note of it. The distance of center of gravity of M by EI diagram. The distance of center of gravity of M by EI diagram. The distance of center of gravity of M by EI diagram from the A point. If you need to find delta A with respect to B, if you want to find delta A with respect to B, then please take the distance from here to here. Area is itself is one type of force. Not believing, you can just check it out. Area of M by EI diagram. M by EI will be what? Into some distance, So Newton meter divided by what? Newton meter square into meter. So here at this point of time, this is a dimensionless quantity, right? It is coming as dimensionless quantity. So remember that here, what we are suggesting that you just try to calculate the centroid of particular area. For particular area, and if you are taking the moment, how to calculate the moment of area? Just take the area into what distance? That is the moment of the area. See what we say, moment of the force. How to calculate the moment of the force? Force is there into distance about this particular point. So moment about A point will be F into X. A very similar kind of things will be performed by the area also. Instead of force, we will be having area. Area into distance, that will be moment of area under M by EI diagram, right? Make a note of it. Right. So these are the statement that will be there. And you can just remember some of the important formula regarding slopes and deflections. Some standard results what we have. A cantilever beam, which is being subjected to point load. We have the maximum deflection at the end point. And what is the maximum slope? See, I'm just drawing the diagram. Something like this. So this will be the deflection at point B. And that will be the slope. This will be the slope, theta B, right? This is the point A, this is the point B, this will be the slope, theta B. Right? We have the standard results. I'm going to prove by many methods, but I'm just telling you, these are the standard results that you must remember actually, And once we have the, cantilever beam, which is being subjected to load, not at exactly at the midpoint or maybe at the free end, but somewhere, some other random locations. So these are the formula, but I don't think that you need this one. You only need this one, this one. These are the important standard results. And again, don't need to remember this thing also. Not required, right? The deflection equations. Again, here also, these are the two important points. You need to remember that. Coming back to the points, how to solve the numericals by using moment area method. By moment area method. Moment area method. We also call this method, my dear friend, as Moore's method. What we call? Moore's method. Try understanding. This is a very simple method, but very important one for our GATE examinations. Whatever the aerospace questions they are asking, mostly we will able to solve the problem by moment area method. Right? Now let's see how we can proceed with that. Here, understand a cantilever beam which is being subjected to some kind of movement. Right? They are asking what will be the deflection at the point B and point C. Very first of all, what will be the deflection curve? The deflection curve would be something like this. It's a kind of parabola, right? The deflection curve would be something like a parabola case. The deflection curve would be parabola, right? Where this will be the deflection at C point. This would be the deflection at B point. But how to calculate, sir? That we can able to calculate by taking our reference. The reference you can take C. In our theory number 1, we have taken the reference to calculate theta B with respect to A. We have taken the reference A point, right? For calculating the deflection at A, we have taken the reference B point. Here also we can take any reference. It's our choice. It's a random choice. But the reference should be selected in such a way that it is very easy to find the slope and the deflection at the selected reference point, right? So I'm selecting my reference point, A point. A point I'm selecting as a reference point. Be patient, you will be understanding after 5 minutes each and everything, but you need to be a little bit patient about understanding the fundamental logic behind this question. A is a reference point. If A is a reference point, draw the elastic curve, first of all the 3 points, draw the tangent, draw the tangent. And one more thing, by here it is nothing but a very fixed support. If it is a fixed support, the deflection as well as slope will be zero. You can remember just like a boundary condition in the fluid mechanics. Here also you can remember that what will be the boundary conditions. Theta A will be zero, deflection at A will be zero. Now if I draw the tangent, I will be getting something like this. If I draw the tangent, I will be getting, this is the tangent at A. This will be the tangent at A point, right? What will be the tangent at B? What will be the tangent at B? What will be the tangent at B? This will be the tangent at B. Or rather to drawing in a different manner. Let me draw correctly. Just wait, just wait. We can draw something like this. So at the A point, as you can see very clearly, we have zero slope, my dear friend. So this will be the tangent at A. What about the tangent at B, my dear friend? The tangent at B would be something like this. This will be the tangent at B. What about the tangent at what we can have this, C point? The tangent would be somewhere here, and my dear friend, the tangent would be this will be the tangent at C point. Getting my point? This will be the tangent at C point. Now, it's very easy to calculate the deflections. You take the point on the elastic curve at the C point. So that is C I have taken. Take the reference point. Suppose you just take the point extended tangent at from the A. What is the extended tangent? What is the extended tangent from the A point? This is the black color, right? So what about this particular difference? What about this particular difference? C, the reference point is A. That means this particular distance will be delta C with respect to A. Because I have taken the reference point A, I have drawn the extended version of the tangent. I have extended this particular tangent, which is being drawn from the point A. As you can see, this will be the tangent. I have just extended it, right? And from there, I have considered one point, and at the C point on the elastic curve, whatever the elastic curve is there, I have taken the point C. C point and A point, whatever the distance is there, that will be the deflection C with respect to A. This is zero, and that is equal to movement of M by EI diagram between A and C, about C. Movement of M by EI diagram, about C, because we need to calculate at C. Whatever it is there in the numerator, that we need to calculate, understand? Go through this particular theory number 2 multiple times. The vertical distance between tangent at A, that is what we need to calculate. Deflection A with respect to B. How to find A with respect to B? Take the point A, where you need to find the deflections, and draw the tangent from other point. And you just try to extend it below the point A. Extended version of this one. And what we got from here to here, the distance between the two tangents at the respective points will be A with respect to B. T means delta, you can write. So it's a very simple theory, my dear friend. Same theory we are applying, right? Same theory we are applying. Now, very first thing is that how to draw the bending moment diagram. This will be the bending moment diagram. Everybody might be knowing from our last class what we have discussed. This is what we have, the M by EI diagram. This is my dear friend, minus of M naught divided by EI minus M naught divided by EI, because there's a no force, so that will be a constant graph will be there, right? That is a negative graph. So what is the basically the moment? First of all, calculate the moment of area of m by ei. So first of all, calculate the area. What is the area, my different? Minus of m naught divided by ei into, this is L by 2, this is L by 2. So total length is what? L. Total moment of area between A and C. Between A and C, between A and C, because tangent we have taken from the A, and another tangent we have taken what? At C. C, A. About C. About C means what? L by 2. So m naught L square divided by 2ei. This will be the simple formula of deflection, my dear friend. This will be the simple formula of deflection, that is coming out to be negative. Deflection C is coming out to be minus m naught L square divided by 2ei. And you can see very clearly that why it is getting negative. Why it is getting negative means, why it is getting negative, because C point is below the A point. As you can see, whatever the tangent is there, the tangent at B, tangent at C is below the tangent at A. That's why it is negative, right? And it is getting deflected in the downward direction. For that purpose also it is negative. But suppose, for example, somebody not interested to take the tangent from A point. Sir, I will be taking the tangent from B point, and I will be very much interested to know this particular distance. This will be what? Delta C with respect to B. Unnecessarily, if you take point B as a reference and you just extend the tangent at B, you can able to find delta C with respect to B. You can able to find, nobody can stop you. Yes, you can find. But for that, you need to know what is the delta C minus delta B. You need to find delta C. We need to find delta B first. Then the total deflection at C would be, see here we are able to find deflection at C directly, C with respect to A, because deflection at A is equal to 0. So that's why I'm saying that selecting a reference point is a very, very important choice. It's a very, very important thing. If you select the point B as a reference and you try to extend the tangent from B point, you will be getting what? Delta C with respect to B. But that is not the final deflection at C point. So final deflection would be what? The final deflection would be, this is the deflection at B. This will be theta A, theta B into L by 2. So final deflection would be deflection at B, theta B into L by 2 plus deflection C with respect to B. Unnecessarily, you will try to extend the sum of these steps. Unnecessarily. While selecting the wrong reference point, unnecessarily, you will try to extend the particular simple problem. Don't do that in examinations, right? Try to select the point. Try to select a reference in such a way that we should be knowing the deflection as well as slope for that reference point. Understand? That's a very simple trick behind this particular theory. It's a very, very important theory also. We cannot neglect, right? So I'm just removing all these points. I'm just telling you, what are all the possibilities of getting the doubt, right? You should not be getting any single doubt. So this complete would be delta C with respect to A. My different delta B, draw the tangent from the A point, draw the tangent and take the reference point. Again, we are going to apply the same theory. Draw the tangent from A, from B point, whatever the deflection is there, delta B with respect to A would be delta B minus delta A. Delta A automatically 0. Area of M by EI diagram and the moment of that area between B and A, not C and B, not C and A, B and A. What is the moment of the area? First of all, find the area. Minus M naught divided by EI into L by 2. That is the moment. That is the area. That is the area into moment. Moment will be about the point B. L by 4 of this particular area between A and B. So this will be L by 4. So finally, what we're going to get? M naught into L square divided by ATI. Right. So make a note of it. This is a very, very important thing. So in this manner, we can solve the problem by moment area method. Very, very important method and one of the very, very important topic also. Right. So as you can see, my different, we can solve the different problem. One problem they have asked in GATE 2014 aerospace. See, for 2 marks, right? While looking at this particular diagram, it looks a very difficult problem, but it is not. Let me tell you frankly, it is not a very difficult problem. Draw the elastic curve. Draw the elastic curve. Between P and Q, there is a no load, there is a no bending moment. And what will be the elastic curve? When there is a no movement, elastic curve will be infinite. For which curve we have the radius of curvature as infinite? For which particular curve we have the radius of curvature as infinite? Straight line. So here to here, there will be some straight line. My dear friend, there will be some straight line. And here it will be parabola. And from here to here, it will be straight line. Once again, it will be straight line. Getting my point? So try understanding what I'm telling to you. Here we need to find the 50 Newton load which is being applied at the center of the beam, magnitude of the slope of the beam at the tip S. What will be the deflection at this particular point? Sorry, slope they are asking, they are asking the slope. See, the slope will be something like this, theta C, theta S. This is a slope at this particular elastic curve. My dear friend, straight line. Somebody might have told you in the childhood days, that if it is a straight line, then whatever this angle is there, this particular end will be having the same angle. Every line, every point will have the same angle. So here it will be theta r. So whatever the theta r will be there, that will be equal to what? Theta s. Getting my point? Theta r will be what? Theta s. And how to calculate theta r? That will be equal to what? Theta r from here. Theta r from here. But we don't know the value, sir. Suppose you in an examination you are not able to remember the standard result case. What is the standard result case? The standard result means a simply supported beam which is being subjected to a load at the mid. Then what is the value of the slope at the support? At the support, there will not be deflections. These are the rigid support, not the flexible support. These are the rigid support, not the flexible support. And we know already the standard results. What is the support at A point and B point? Already we know that. PL square divided by 16 EI. Right? If you want to know how we are getting, you are welcome to the moment area methods. Just check it out. Nothing we have to do, draw the bending moment diagram, M by EI diagram. This will be the M by EI diagram. This will be, my dear friend, M by EI diagram. And how to calculate the moment? That is a quite easy task for us. How to calculate the moment? From here, exactly M by EI diagram. But here, what is the value of bending moment? What is the maximum bending moment that you are observing at Q, at R, at S, and as P? What is the value at Q at particular O point? What is the value? So value, we know that M at O will be WL power 4, WL by 4. W is what? 50, L is what? 1.2 divided by what? 4. So 15 to 1.2 divided by 4. I am getting what? Around 15, 15 Newton meter. Correct? 15 to 1.2 divided by 4. So 15 Newton meter I am getting. 15 divided by EI. That is my M by EI diagram. I need to find theta r. How to find theta r, my dear friend? Draw the tangents from both the points. From here, it will be 0. And from here, draw the tangents. Draw the tangents. This is a tangent at R. This is a tangent at O. Getting my point? And this particular angle would be theta r with respect to O would be the angle theta r, because theta O already we know that it is 0. Symmetric loading condition, So at the point of maximum deflection, slope will be 0. Getting my point? Try understanding. You'll be understanding each and every concept. Now, theta A r with respect to O will be what? Theory number 1. Theory number 1 is for slope, Area of M by EI diagram. Area of M by EI diagram. See, problem you can solve within a fraction of second once you know the particular formula directly. But in precise situations, there is a high probability that we might forget the formula. In that situation, I'm just telling you what you can have. Area of M by EI diagram between what? O and R. That's it. Theta R minus theta O is 0. Area of M by EI diagram, what is the value? 15 divided by EI into what? What about this particular distance? 0.6. That's it. Finish. So 15 into what? 0.6. That is the 9 divided by EI. Once we got to know theta r, directly put the value and get the answer. So 9. That is a unit also you need to take care of. 9 divided by EI. So 9 divided by E is what? 200. into 10.9. Moment of inertia would be what? Moment of inertia, you try to calculate BDQ by 12. What is the moment of inertia? Moment of inertia would be 10 into 16 cube divided by 12. Because bending is happening about the what? X axis, not about the y axis, right? The bending is happening about the IXX. So moment of inertia should also be considered like about that particular axis only. Getting my point? Once you calculate, you will be getting the answer as 0.125. You can check it out. You will be getting the answer as 0.125. Moment of inertia would be my different 10 into 6q divided by 12. That will be like mm to the power 4. That will be 10 to the power minus 12 into 200 into 10.9. That is going to be 36. So 9 divided by something like that, 0.25. Area of M by I diagram. What you are doing the mistake? Area. What is the area? What about the area? It is not a rectangle one. It is a triangle one. So half of base into height. That will be the complete area. 1 by 2 into 1 by 2 into 1 by 2. So when you calculate that, you will be getting the answer as 0.125. But take care of the units. When you are putting 9 Newton mm, 9 Newton meter, each and every unit of E and as well as I will be in the Newton meter also. E value is what? 200 gigapascal. 1 gigapascal is what? 10 to the power 9 Newton per meter square, my dear friend, right? Similarly, you try to convert moment of inertia also. So I hope that you try to, basically you are getting the proper, basically the concept behind the moment area method, right? Thank you all.